Ladies and gentlemen, boys and girls, we are now going to talk about friction, which I find actually kind of interesting. It seems like a very, very mundane subject, but I'm kind of into it. So let's check out what friction is all about. Why do we have friction? Well, the science books tend to show this little diagram where at a microscopic level the surfaces are very rough, even though that on a macroscopic level they might seem really smooth. And so that roughness is what causes friction. Let's look at that a little more carefully. Over here I have a detailed, carefully drawn scientific view of this surface. So it's pretty rough, and when the objects are at rest, you can imagine one of them sort of being settled down on top of the other one, and the little peaks of the top object are settling into the valleys on the surface of the bottom object. Then when you start pulling the objects along, you can imagine the peaks of the top object kind of bumping along the peaks of the bottom object. I'm explaining it that way partly so you can see the difference between static friction, which can be greater, generally is greater than kinetic friction. Why? Partly because the objects are simply in a stable situation where these little peaks and valleys are kind of interlocking, whereas when it's moving, they're bumping over the tops of those peaks and valleys. That's really an issue of potential energy. Once you overcome the static friction and raise up this object so that it's bumping along on the top of the ridges and valleys of the bottom object, then you've overcome that kind of potential energy deficit, and the kinetic friction is lower. But there's something else happening. So I've drawn these really lame atoms here. And my intent is to indicate that the atoms between the top object and the bottom object are actually forming bonds. They might be hydrogen-type bonds, or they might be more substantial kinds of bonds, but typically they're of the intermolecular variety, the van der Waals forces and so forth. Nonetheless, those are real bonds that have real sticking power. When more of the surfaces of the top and bottom object are in contact, such as here, as opposed to when they're bumping along over each other, there's more surface area in contact, and those molecular bonds can form more readily. The book actually refers to what happens when you have two objects that are very, very smooth, and they actually form what are called spot welds. For example, you have two carefully polished metal surfaces, very, very smooth. You stick them together, and they will actually stick very tightly together. If you have glass on glass, again, very smooth, they'll stick very tightly together. So you've got both kind of macroscopic, not quite macroscopic, but large microscopic forces involving potential energy and the shape of the surfaces, and then you have atomic scale forces that are also causing friction, and both of these sets of kinds of forces are greater when two objects are at rest relative to each other, as opposed to when two objects are moving against each other. Okay. So kinetic friction is less because the two objects are kind of bumping along rather than locking peaks and valleys, and the intermolecular forces, IMF, when the object is moving fast, don't have time to form. That's an issue of kinetics, as well as there being less surface between the two objects when one's bumping along ridges and valleys against the other. So there's less time for those bonds to form and less surface area as the one object is bumping against the other. Okay, you can look up cold welding in Google and you'll find that what I said is the case. The objects will actually stick together. Okay. Notice also that static friction, abbreviated Fs, is variable. How is that? That simply means the harder you pull, as long as the thing is not moving, the more friction force there is. How can the force be variable? Well, one explanation is that as you're pulling this object this way, you're kind of pulling up, raising up the top objects as the peaks and valleys slide against each other. And the more you pull, you've essentially expended some energy raising one object up relative to another. But another explanation is at the atomic and molecular level. You're stretching out bonds. You are literally stretching molecules of one substance that want to stick to the other object, and as you're pulling harder and harder, you're stretching out those bonds more and more until finally they snap and the objects start moving against each other. All right, well, I hope you haven't been too bored by my little pet subject of friction, but that's really an explanation of why the static friction force can be variable and tends to be greater than the kinetic friction force. When we talk about a static friction coefficient, mu sub s, that refers to where the static friction is at its maximum. And that's why the static friction coefficient is always less than the kinetic friction coefficient. This graph in Survey shows the variable nature of the static friction force. Then when the force is reached that finally breaks the two objects apart and begins one sliding over the other, the friction force goes down to a lower level, which is the level of the coefficient of kinetic friction. Okay. What direction does the friction force point? It always points in the direction opposite to the motion. What direction does static friction point? It points in the direction opposite to the motion that would occur if there was no friction. And I hope that's clear, and that's really all I have to say about friction. Thanks.